Hi, my name is Alex, and I'll be talking about a deep learning project analyzing horse racing data. The objective of this project will be to use various different models and architectures to attempt to profitably predict winners of horse races based on the data supplied. The data that will be analyzed is a subset of the Kaggle dataset Horse Racing, covering the 2020 portion of data and about 150,000 different racing records across just under 15,000 races. In terms of cleaning and processing, some steps were to drop unused features, such as the country code, as well as conversions between measurement systems describing the same data, and transforming each observation to include the relevant attributes of the race referred to, as well as including details about other runners in the race through merges and lambda functions. Some initial findings were that the race's CSV didn't have a list of all the runners referred to in the race, and that the link between horses was simply that they had the same race ID. Many variables in the initial exploratory data analysis didn't have a clear trend when filtered for winners only, and thus no clear correlation to winning. But Saddle had an interesting result where the win rate is almost perfectly sorted in ascending order, despite Saddle's 1, 2, 3, 4, and 5, so the starting positions 1, 2, 3, 4, and 5, having the same amount of samples. The benchmarks used include the standard binary cross entropy and F1 score used for binary classification, as well as a custom profit loss function that I created in order to simulate the winnings across the test dataset if the predictions by each model were followed. This model essentially looped through the test dataset, and if a horse was predicted to win by the algorithm, this would look at if it did win. If it did, then it would add the profits to its score based on the payout odds, and if it didn't, it would subtract 1 from the score to simulate losing. I used two naive models, simply choosing the favorite to win, and simple linear regression on the initial horse's data. These benchmarks yielded non-stellar results, with the linear regression being slightly better based on my profit loss metric, but still losing over 250 units. However, this also had a slightly worse F1 score, and the all winners sanity check ended up clearly being the worst. My first deep learning architecture was a simple dense model that simply funneled the data sequentially through a series of leaky ReLU hidden layers. This encoded all relevant categorical data through one hot encoding and funneled all inputs through to a sigmoid output as a confidence or probability about whether the horse is going to win. If this final number was higher than 0.5, then it was predicted to win. The second architecture involved processing the categorical data and continuous data differently in a wide architecture before concatenating them back into sequential dense layers. The categorical data was entity embedded individually, reshaped combined with the continuous data, and filtered through hidden layers, including dropout, to reduce overfitting. Some validation metrics from both deep learning models are shown here. It's interesting to observe that with each epoch, the validation and loss and area under curve trend to getting worse, implying that there is an overfitting problem in the current architectures, with the final models often being chosen from epochs 5 to 15, where the simple one hot model outperforms and the validation error is the lowest. This dropout might be the reason that the entity embedded model doesn't deteriorate as much over time, as it is less overfitted to the training data. But nonetheless, it still overfits more than the initial 5 to 15 epochs. The preliminary results are very positive for the deep learning architectures, actually profiting over 4,000 units on most runs with a much higher F1 score, improving by almost 60%, even against the relatively better naive model than both of the naive models. For perspective, the profit over time graph when running the custom profit loss algorithm is shown in the bottom left, with the simple one hot network graphed against the linear regression outcome, and we can see that there is a massive difference. In order to address the overfitting issue, more dropouts and hyperparameter tuning on the number of neurons, layers, and activation functions will be used to improve the model. Thank you for watching this presentation.